So let's go back and look at our KSPs. We've talked about the soluble salt version where, even though we say the word infinity, we really mean numbers like 5 or 10. And look instead at this class of compounds called sparingly soluble salts. There's one. There's chalk dissolved in water. Notice, by the way, that for the most part, these sparingly soluble salts are multiply charged. Notice that when I put them into water, their Ks aren't infinity. They're not even 5 or 10. They're really small numbers. They're numbers like 10 to the minus 28 or 10 to the minus 10 or 10 to the minus 40. In other words, they suggest excuse me, that not a lot of salt is going into water. They suggest that the amount of lead ions, that the amount of sulfate ions is really, really small. Well, we don't want to say the word really, really small anymore, so we'll be learning in a few minutes the math for solving this. We're going to learn in a few minutes that it's not really, really small amounts of lead in water. It's 10 to the minus 14 molar in water, 10 to the minus 14 molar in water, 10 to the minus 5 molar in water, 10 to the minus 5 molar in water. This one's a little different. 10 to the minus 4 or so, 10 to the minus 4 or so. But in all of these cases, as I solve these problems using my Rice expression, we're going to find out that these amounts are small. So small, in fact, that on a certain level, we think of them as being negligible, which is why when I drink drinking water, or I drink glacial ice water, or I drink something that tastes pretty good that I buy in a little bottle from the store for way too much money, like my Perrier or something like that, I am drinking pure water, yes, but it's pure water with some tasty ions sitting in it that I don't know about. It's just tasting better, and so I can live with it. But understand the profound difference between those tasty, sparingly soluble ions and the notion that I'd put a whole bunch of salt in your water and make you drink salty water. It's because the K values are so fundamentally different. We will be concentrating on the sparingly soluble salts and figuring out their concentrations as I show you how to do this using the Rice expression. So, if you remember back at the very beginning of the lecture, I said, you know, of all the different kinds of chemical systems in the world that we might have taken a look at, I decided that the first one we'd look at for water chemistry was salts going into water. And I told you it was because it was the easiest case, because it was the case where it was a solid I was dumping into water, and I could ignore the denominator. That makes my math easy. That's the good news. The bad news is that it's not quite so simple because there is a level of complication we have to deal with. And we can see pretty simply what that level of complication is as we take a look at the forms of different kinds of salts. Salts typically come like this stoichiometrically. You put one cation, one anion together like sodium chloride, that's a salt. You put a situation together in which you have multiply charged species like a calcium and an oxide, still of the form AB. But then we have these other cases that make things a little bit more complicated mathematically. I can put one magnesium together with two chlorides, Mg double plus Cl minus 2, and you have MgCl2. Or I can put together a situation where I have a doubly charged species like sulfide and a couple of sodiums, Na2O. These cases here as well. This one right here would be something like aluminum chloride, because aluminum's plus 3, or in this case particularly, here's something like potassium nitrite, because the nitride is minus 3. Here is something like aluminum oxide. Here is something like calcium nitride. These are all salts. I have to be able to write their equilibria. So let me write equilibria for some of them. Here's AB, going to make A plus and B minus. Here is A2B, going to make A plus, but I've got two of them, and B double minus. Heck, here's A2B3. It goes to make two A plus 3s and 3 B minus 2s. Now that I have these expressions, I can write their K values down. I don't have to worry about the solids, but I have to worry about the coefficients. KSP for this is equal to A plus times B minus. In this case here, KSP is equal to A plus squared B double minus. In this case here, KSP is equal to A plus 3 squared B minus 2 cubed. Notice how common the forms are. The only complication is that I have squares and cubes occasionally, depending upon how many of the atoms I have in balancing the composition, and consequently in terms of the coefficients that sit in the equilibrium expression.